The question says a steel stanchion is built of a rolled steel joist of I section 45 centimeter by 20 centimeter. All right. This is the I section and it is 45 centimeter by what? By 20. That is, the depth is 45 and the width is what? Is 20 centimeter. That is the base. All right. So of I section 45 centimeter by 20 centimeter united by 1.5 centimeter thick and 30 centimeter wide plates fastened on each flange. You know, when we talk about flange, we have the top flange of the I section and the bottom flange of this I section. So, and then we now have a plate that is placed on it, that is placed on the top flange and on the bottom flange. So the dimension of that plate now, that is what they are trying to give us there, and which is 30 centimeter wide. You can see from this point to this point is 30 centimeter wide, and the thickness, that is the depth, is 1.5 cm. I hope we understand. All right. So now the length of the stanchion is 5 meter, okay, and is freely supported at both ends. So for each for the I section, ISS is given to us, that is the moment of inertia of the I section about the neutral axis, is given to us to be 35060 centimeter to the power of 4. So now the first question says we should find the moment of inertia of the enlarged section about the SS axis. And the second question says the greatest central point load the beam will carry if the bending stress is not to exceed 120 meganewton per meter cube. And the third question says minimum length of the 30 centimeter by 1.5 centimeter plate. All right, let's start with the first question. All right, so for us to solve this question, since we already know the moment of inertia of this I section himself, so the thing we will just do is just to get to work. So we can just take this bottom plate to be our first rectangle, and this our top plate to be our second rectangle. All right, now the next thing that we are going to do now is to calculate the moment of inertia of this enlarged section. So let's go for the moment of inertia. So the moment of inertia, so let's take this as a moment of inertia of the enlarged. So this will be equals to the moment of inertia of this I section. The moment of inertia of I section about the XS axis plus the moment of inertia of the plate about the SS axis. The moment of inertia of plate about the SS axis. All right, so let's continue here. So this will be equals to I don't know if this space will contain it. I just want everything to be on a straight line. Okay, let's try it out. So the moment of inertia will be equals to, we know the moment of inertia of the I section about the SS axis is already given to us to be 35060. I'll need to reduce my writing a little bit. All right. 35060. All right, that's it. So now plus, now we know we have two plates. We have the bottom plate and we have the top plate. So let's find the moment of inertia of this plate. So don't forget, of a rectangle is going to be BD cubed all over 12 plus the area into either y1 minus y bar or y bar minus y1 all squared, right? So now I will just be applying the formula directly. So now our BD cubed, our B is the base and our D is what? The depth, right? So B is 30 for the first rectangle. So it's going to be 30 multiplied by 1.5 cubed divided by 12 divided by 12 plus the area. The area of this first rectangle is 30 multiplied by what? 1.5. And 30 multiplied by 1.5 is nothing but what? 45. So we are going to have 45 here. Into, now let's check what will be the y bar, that is the moment of inertia from the bottom to the top of this rectangle alone is going to be what? 1.5 divided by 2, right? So and the 1.5 divided by 2 is 0.75, right? So that is our y1. That is going to be our y1. So now what of our y bar? So our y bar is the moment of inertia from the bottom to the what? To the neutral axis here. That is about this SS axis, right? So now how do we do that? We are going to sum, since the plate is here and another plate is here, and we already know the moment of inertia of this. So now we can sum everything together. If we sum everything together and we divide by 2, we are going to have our y bar. So our y bar is going to be 1.5 plus 45 plus 1.5. That is going to give us what? 48. And if we divide 48 by 2, we are going to have 24. So you can see that our y bar, which is 24, is greater than our what? Our y1. I hope we understand. So now this formula is going to be y bar minus y1 all square. So our y bar is what? 24. So it's going to be, so it's going to be 24 minus 0.75 all squared. I hope you understand how we come across 24 and 0.75. All right. So now, so plus, I don't know if I should continue. Then let's just continue, please. I just want everything to be on a straight line so we can see it clearly. All right. So plus the moment of inertia of the second plate now is going to be BD cubed over 12 multiplied by area, then into either y bar minus y2 or y2 minus y bar. Don't forget, our y bar is what? 24. If you have been following this lecture from the beginning, you already know what y bar is. All right. So now, this is going to be BD cubed. So BD cubed is the same thing as what we have here. So it's going to be 30 multiplied by 1.5 to the power of 3 divided by 12 plus the area. The area too is going to be 45. Then into our y bar is 45. Then our y2. Our y2, for us to get our y2, is going to be what? 1.5 plus 45 plus 1.5 divided by 2. Right? So if you sum all of that together, you are going to have what? You are going to have 47.25. So 47.25 is greater than our y bar. So it's going to be 47.25 minus 24 all squared. So this is how to calculate the moment of inertia for this question. So by the time you sum everything together, so here you are going to have your moment of inertia will be equals to, we are going to have 35060 plus, so if you sum everything that we have here together, you are going to have your answer to be 24,333 point what? 0.75 plus, if you sum everything that we have here again together again, you're also going to have the same answer as this. It's going to be 24,333.75. all right, so this will be equals to, if you sum everything together now, you are going to have your answer to be 83727.5 centimeter to the power of what? 4. all right, so we have answered the first question. So we are done with the solution of the first question. Please, I believe we understand this. So let's solve question number 2. Question number 2 says the greatest central point load the beam will carry if the bending stress is not to exceed 120 meganewton per meter square. So for us to solve that, you are going to recall that from the question we are told that the length of the stanchion is what? 5 meters, and it is freely supported at both ends. So it means that this stanchion is having a what? A simple supported beam. So the load now that's what they said, the greatest central point load the beam will carry. So it means if we have a point load on this stanchion, and which is freely supported, now what will be the load? What will be the load that? So that is what we want to try to calculate, right? All right, but don't forget that for us to solve this question, you are going to apply the maximum bending moment. If we have a simple supported beam that has a point load, that carries a point load, what is the formula for the maximum bending moment? So the maximum bending moment there is going to be equals to WL divided by what? By 4. All right, so now the next thing is this. We know the length, right? The length is 5, right? So now this is going to be equals to 5W divided by 4. And 5 divided by 4 is going to give us 1.25. If I'm not mistaken, yes, 1.25 W. So that is what we are going to have. All right. So what will be the unit? Since our this thing is in meter, so this one is going to be Newton meter. All right, so that is it. Now that we have gotten the maximum bending moment, all right, now that we have gotten the maximum bending moment, so now the next thing we are going to do is you are going to recall from Fleischer equation. From Fleischer equation states that maximum bending moment all over what? Moment of inertia equals to the maximum stress all over what? All over y max, right? All right, so now we know what our maximum bend moment is. We know what our moment of inertia is. Our maximum stress is already given to us to be 120 meganewton per meter square. So our y mass is going to be 24. If you sum all these things together and you divide by 2, I'm going to have it to be what? 24. But don't forget it is in centimeter, so we need to take it to meter. So now if we substitute, we are going to have 1.25 W all over I, and our I, which is our moment of inertia, is going to be 83727.5, which is going to be equals to our stress, which is 120 times 10 to the power of 6 divided by our y mass, which is what? 24, then times 10 to the power of what? Minus 2. All right, so this is what we are going to have. So if we make our W the subject, W will therefore be equals to this cross multiply this will come back. So we are going to have 120 multiplied by 10 to the power of 6 times what? Times 727.5. Then everything divided by what? Divided by 24 multiplied by 10 to the power of -2 multiplied by 1.25. So if you do the math, our W, if you multiply everything here together and you divide by everything that we have here, I'm going to have your answer to be 3349349 what? 10 Newton. All right. So, but you can decide to take it to kilonewton, right? So if you do that, you are just going to divide by 1000. So this is going to be equals to 1, 2, 3. So it's going to be 334.910 kilonewton. So this is the solution to the second question. All right. So now we are going to go for the third question. For us to solve this third question, we are going to assume something. So let's go. Now, suppose this plate, these two plates, they are absent on this I section at a distance of S meter. So the meaning of that is this. It means that the maximum bending moment. It means that the maximum bending moment must exceed the moment of resistance of the I section. So here, what we are going to do is we are going to firstly calculate the maximum bending moment, right? So where we are going to be assuming the moment of inertia here to be the moment of inertia of the I section. So we know that if we do that, the maximum bending moment will be greater than the moment of resistance of this I section. I hope you understand that. So from our formula, we know that the formula for if we make our M the subject here, we are going to have M to be equals to maximum stress over Y multiplied by what? I. So this will be equals to our maximum stress is 120 times 10 to the power of 6, then times our I. It is the I of the moment of inertia of the I section itself, which is what? Which is 35060. Don't forget it is in centimeter to the power of 4. So you are going to multiply by 10 to the power of -8. I hope you understand that. So as for us to take it to what? For us to take it to meter. So this will be divided by our Y now. So the Y will still remain the same, which is what? 24, right? So now it's going to be 24 multiplied by 10 to the power of -2. All right. So now this will be equals to what? This will be equals to, so if we do this, we are going to have the moment now to be what? 175 300 175 300. Yeah, I believe it's correct. So now this the unit is going to be Newton meter. So that's it. All right, so that's it. Now don't forget that again that we are told that this plate, the stanchion is simple supported, right? All right. So the length of the stanchion is 5 meters and it is simply supported. The stanchion is simple supported. So now if it is simple supported, it means we are going to have a simple support here. Let's say something like this, RA, and another simple support here, which is RB. Now don't forget that we said it is at a distance of what? S. So let's take something like this. So if it is like this, we are going to have this to be W load, because we don't know what W is. So it means that from this point to this point is going to be S. So it's going to be S. I hope we understand. So now, if you calculate your reaction at A and reaction at B, they are going to be equal. It's going to be W over 2 here, and then we are going to have W over 2 because the load is acting at the center. I hope you understand. All right, so I believe we understand all this analogy. So this is S, and this one too is going to be S. Same for the top and the bottom. All right, so now if we now take moment now to this point now, is either we take our moment towards this direction or we take it towards this direction. So anyhow we are taking our moment there, the maximum bending moment at S meter from each support is going to be what? So the moment will be equals to what? It's going to be equals to either W is going to be W over 2 multiplied by what? By S. So W over 2 multiplied by S. So that's what we are going to have. Now that our M, this is our M here, we are going to have 175,300, which is going to be equals to W over 2, and our W is 334910 multiplied by what? By S, then everything divided by what? By 2. All right, so if we make our S there the subject, S will be equals to 2 multiplied by 175,300 divided by what? Divided by 334910. So if we divide this, our S is going to be equals to 1.05 meter. All right, so that is our S. So it shows that the value of our S is going to be 1.05 meter. All right, so now I'm going to clean. All right, so we are done with the calculation. So now you take note of this. I wrote S, leaving 1.05 meter from each support. As you can see it clearly, from here to here is 1.5, from here to here is 1.05 rather. So for the middle now, because we know that the total length of the stanchion is 5 meter, so it's going, if we add one S plus S here, that is 1.05 plus 1.05, that is 2.1. So if you subtract 5 minus 2.1, you are going to get 2.9 meter. So the cover place should be what? Should be provided. So this is the solution to the third question. I believe we understand this question clearly. So stay tuned for more questions. Thank you.